Hello everyone. Today's learning objective is students will be able to describe systems, chemical reactions, and balanced chemical reactions. Please take out your notebooks to write notes and open IS-1 Experience 3 Nearpod on your screens. Thank you. The learning objective is students will be able to describe systems, chemical reactions, and balance chemical reactions. Please take out your notebooks to write notes. The warm-up for today's lesson is: what does changing the number of protons change in an atom? Please look at your notes and answer the following question. Thank you. In the notes, please make sure you write and draw everything. A system is an object that you are studying. It's the thing that you care about in any science experiment. Usually, we talk about systems and surroundings in reference to the item we are studying and the container, and sometimes the room that we are working in. A system can include three different kinds depending on the container and the enclosure of it. First off, we have an open system, which is where both matter and energy can freely move. This is usually in reference to an open container and some sort of material like glass or metal that allow the transfer of heat energy to go inside and out. Second, we have a closed system. This is where matter cannot move, but energy can move. The easiest example of this is any sort of item with a lid. And lastly, we have an isolated system. An isolated system is where not only is there a lid, but there's some sort of material covering the system or the container so that there is no amount of energy going in and out, and the matter cannot also go in and out. The most common example of this is styrofoam. Styrofoam is an excellent way of preventing heat loss or gain, and you can also cover it with a styrofoam lid, which you'll see this sometimes in cold packages being shipped across country. But another common one that you might have with you is a type of water bottle. One of the most common ones originally was the Thermos brand, but in terms of water bottles, this may also be called a hydro flask or something else of the sort, where it is a metal outside and a metal inside, and then there's some sort of lid on top. Usually, the outside temperature of your water bottle is warmer than what the inside is. And even if you put that water bottle in the refrigerator, let's say, the outside will get cold, but the inside temperature will basically not change very much. And so this is an example of an isolated system. In chemistry, the flow of matter is modeled through equations that are similar to an equation you would use in algebra. In chemical equations, the numbers and types of atoms are equal on both sides. The masses on both sides of the equation must be equal. The number of atoms on both sides of the equation must also be equal. Now, it's not listed here, but hopefully you'll notice that these statements follow the law of conservation of mass, where no mass has been gained or lost, but somehow we have to keep track of all of the numbers of atoms so that the masses are the same on the left-hand side, called the reactant side, and the right-hand side, called the product side. There are a few ways that we do this. First off, I'm going to start with the right-hand top side, which talks about subscripts. Subscripts show the number of atoms in a compound. So we represent atoms using one or two letter abbreviations, such as in this example, the letter K stands for potassium, and the letters Cl stand for chlorine. The lower number 2, which is kind of the opposite of an exponent called a subscript, is where you indicate how many atoms there are in one group of that compound. On the top left of this picture, it says coefficients are in front of chemical formulas to indicate the number of atoms or molecules. The term coefficient is actually a math term. You see this in common algebra equations such as 2x equals 4. The number 2 times x, but the number 2 refers to a number called a coefficient. It's a number used to multiply something next to it. In this case, the x. In this example, we have the number 2 as a coefficient next to the letter K. This indicates that there are two groupings of potassiums. Now, since in this case, potassium is not necessarily a compound because there's only one of them, there's no subscript, then we simply multiply 2 times 1, which means there are 2 potassiums. For the chlorine, in a similar manner, there are a total of 2 chlorine atoms. On the right-hand side, we once again have a coefficient of 2. But the coefficient of 2, again, applies to everything to the right of it. This indicates that there are 2 groupings of potassium chloride molecules. Or technically we call these formula units. But 2 Ks and 2 Cls on the right-hand side total make the left and right-hand side match. we're going to practice a type of skill that we're going to see in much more depth in a later unit. But for now, let's just go ahead and give this a try. Let's go ahead and read the directions. Iron, Fe, reacts with oxygen gas, O2, to form rust, Fe2O3. Balance the equation below by writing in the coefficients to ensure that the same number of each kind of atom appears on both sides of the equation. Some of you might be able to do this really quickly, but let me explain this and show what it is I'm talking about. Okay, here's the idea. If you'll notice, there is no number next to the Fe. This means that there is no subscript. So that means I'm only starting out with one of these Fe's here. On the right-hand side, we do have a subscript, which is the number 2. What we need is for the number of Fe, or iron, the number of atoms of iron to match. What we have to do is multiply. We cannot add, and we cannot put a subscript. We are only allowed to put a coefficient. Remember, a coefficient is written in this area to the left of the formula of the atom or compound. So the question is, 1 times some number is equal to 2. What is that number? Hopefully you can quickly see the answer is 2. Let's go ahead and draw or type the number 2 next to the Fe on the left. Okay, now I'm going to erase my work for this one because I want to pay attention to the oxygen now. Now we have the number 2. And we also have the number 3. Okay, what do you guys think? We need a number that can be multiplied together to make 2 and 3 the same number. Now in math class we called this the least common multiple. Okay, let's go through our multiples just to make sure you are comfortable with this idea. Okay. All right. So our multiples of 2 are 2, 4, 6, 8, and 10. Our multiples of 3 are 3, 6, 9, 12, and 15. Okay. Which smallest number is the same in both groups? Okay. All right. Hopefully you can see that answer is 6. So what we need to do is make both numbers multiply to turn into 6. Let's go ahead and do that. Ready? 2 times 1, 2, 3. 2 times 3 is 6. So let's put the number 3 as a coefficient for our oxygen. Let's go ahead and do the same thing for our oxygen on the right. 3 times 2. Great. Unfortunately, we now have a problem. Our problem is this coefficient of 2 on the right-hand side also applies to our subscript for our iron, not just our oxygen. That means that 2 times 2 is actually now 4. Uh-oh. So, we're going to have to fix our coefficient on the left-hand side now. And this is actually what happens when we do balancing equations. Okay, so once again, we're going to start over. We have 4 on the right now, not 2. So what we need is 1 times something is now equal to 4. And hopefully you can quickly see that the answer is now going to be 4. Okay, everyone, this is the answer. 4, 3, 2. In the next slide of notes, we talk about combustion and what it is and what there are with some indicators of colors. Please do write and draw everything on this slide. Somehow we need to indicate on the bottom picture a blue flame versus a yellow flame. You can draw either one if you just have a pencil and put like blue and yellow, but one way or the other, you need to somehow remember the colors because those are very important in lab. In combustion reactions, oxygen gas reacts with a molecule, often releasing energy in the form of both heat and light, or what we call a flame. The fuel that burns is often a hydrocarbon, containing atoms of both hydrogen and carbon. The products of the reaction depend on the amount of oxygen present. In a complete combustion, there is sufficient oxygen in the environment, and the products are carbon dioxide, water, and heat. In an incomplete combustion, the products are the same, and carbon monoxide is also produced. An incomplete combustion happens when there is limited oxygen in the environment. And again, in the pictures, a blue flame is an indicator of complete combustion. We as humans can breathe carbon dioxide and water just fine. However, an incomplete combustion, which contains a yellowish orange flame, also produces carbon monoxide, which is lethal to humans. Please fill in the blank using the notes you just took. In our last slide of notes, we are now going to talk about nuclear reactions. This is in reference to nuclear bombs and nuclear power plants. During nuclear reactions, certain forms of matter can be created or destroyed, and matter is converted into energy. Consider the equation E equals mc squared, where m is the mass in kilograms and c is the speed of light in a vacuum, which is 300 million meters per second. Since c is squared in the formula, making a very big number, you can see that converting a small amount of matter releases an enormous amount of energy. Matter is destroyed during fission, fusion, and the decay of radioactive elements, such as uranium. The purpose of this slide is to indicate that while most laws in science can be considered true and accurate basically all of the time, this is one example where the law of conservation of mass does not apply. But again, this is a very unusual reaction where this happens in very large scale nuclear reactions and in the sun. Please watch this video with some examples showing some radiation sources and the use of a Geiger counter. In the following video, you will see an example of a cloud chamber, which is where you fill it with some alcohol usually, and a light source as shown here, and a radiation source. And you can see the paths that the radiation travels from that source. Please take a moment to watch this video. Lastly, did you meet the learning objective for today? Please choose letter A if you did not attempt to learn, all the way through E if you did very well. Thank you, everyone, and I will see you next time.